Hey, welcome back, guys. This is my last video in the topic of general equilibrium. Soon we'll be off to acid-base equilibrium and such, which might be more exciting. I don't know. Yeah, it is. In any case, this topic is called LeChatelier's principle. Um, let's see. I think the book defines it. I defined it in my notes, lecture notes. You'll see Wednesday. But for here and now, let me say nature loves things to be balanced out, and she'll do whatever she can to keep things balanced out. And if you try to mess with that balance, she will work against that balance in a sense. She'll do whatever she can to restore conditions to where they were, could be, should be. Who knows what should? The equilibrium constant speaks, I guess, quite a bit to that. So does the temperature. Alright, well, in any case, let's just get into some examples. Here's a general equilibrium, a gas phase equilibrium. I have 173 kilojoules plus some compound A, 1A, and it reacts in equilibrium to give B compound and 2C particles, molecules, who knows. The constant for this, honestly, don't tell anybody, but I just made all this up, is 0.11. But I could imagine a realistic scenario where this is the case. Let me think about, for one thing, is this endothermic or exothermic? Do I have to put energy or heat into this system, or does it come out of the system? Well, if you've been following my arrow, you know the answer already. It's endothermic. But regardless, let's go through a few problems and pose the hypothetical but realistic question. How will the equilibrium shift? All right, so I have a balanced mixture. Everything's good, coming and going. My constant's 0.11 kind of implies to me that I have relatively fewer products and relatively larger amount of reactant at this particular temperature. I don't even know what the temperature is. How will the equilibrium shift? I'm sure it's going to move one way or the other. I'm going to throw things out of balance. If I add more of this compound A to the mixture, well, here's the way I look at it. Everything's all nice and equilibrated. Everything's happy and coming and going. The rate of the forward, the rate of the backwards is the same, although it looks like I probably have a whole bunch more of this and a little bit of this, but it doesn't matter. But if I add even more of this, I will unbalance the equilibrium. I will throw things off. I will push Mother Nature to one way or another. What she will do is take some of that extra A that I just added sort of artificially, or at some point in the future I add more A, that's not quite balanced, that's too much A. So what she will do is she will, if I were to do a reaction quotient for this, I'd have too much, I guess it would be, my Q would be even smaller than 0.11 now, and she'll take this stuff and she'll go this way to create more B and 2 more C's. So in other words, I say the equilibrium will shift to the right if I add too much of this reactant. Let me see one. Here's a similar question. So I'm just going to go with the same equation again and again. How will the equilibrium shift if more B is added to the mixture, to a mixture already at an equilibrium state? Well, if everything's all balanced out and hunky-dory and happy and go lucky, then I throw things off by somehow adding more B. Adding more B is too much B. In other words, the Q would be larger than 0.11. In any case, this is too much B, and what nature will do is she'll try to take some of that and go back this way to produce more A. In so doing, she'll also consume 2 C's to take one of those B's and go this way to create more A. Yes. And giving off some heat too, I suppose. But in any case, it'll go backwards for a while until enough A is created so that the ratio between this squared in the upstairs times this in the upstairs divided by this in the downstairs still equals 0.11. So that's the key. The equilibrium constant must still be satisfied. And if you throw in too much of one reactant or too much of another reactant, she will shift this way to get rid of some of this, or she'll shift this way to get rid of excess A, so that the ratio in that mathematical sense we've defined is still 0.11. Next problem. How will the equilibrium shift if C is removed from the container? Somehow we have a way of selectively removing capital C. So if I take out some or all of this capital C stuff, I leave a blank there, a void, an emptiness, a vacancy, and what nature will do is she'll try to come in and fill in that reduced amount of C. She'll never be able to make back up, probably, in this gas phase equilibrium, she probably never will be able to make up what was taken away, but regardless, she'll take some of this and some energy, and she'll go this way to make more B. It's kind of a sidebar, but more importantly, she'll make some more C, which was removed from the system. So if you take a reactant away, she'll move in the direction to fill in that reduction that you just created. I know this is a bunch of hand waving, but I hope it makes a little bit of sense. I can kind of imagine it if I think about each quantity as an amount, and she likes this certain balance to the mixture. How will the equilibrium shift if the temperature is increased? Well, here's the story with temperature. If you know it's endothermic or exothermic, you just treat that word energy, that word heat, or that number of kilojoules going in, endothermic or coming out. If it were exothermic, it would be written over here, as a reactant or product. So if I jack up the temperature by adding, in a sense, kilojoules to the system, so I add too much energy to the system, Mother Nature will take that excess and she'll take some of this as well, and she'll shift this way to create a whole bunch more of this and more of this, in a sense to reduce the amount of heat that I'm adding to it, also consequently reducing the A, increasing both the B and the C if I increase the temperature. Yeah, and you always have to think with these questions about the opposite question. What if I chilled this container, made it colder? If I had an equilibrium mixture all happy and in equilibrium, that's redundant, sorry, and I make this colder, this isn't a reflection of the temperature, but in a sense the temperature removes kilojoules or removes enthalpy from the system, making this smaller. Then B and C would fall this way, in a sense, to create more A and more heat to try to fill in or redo or undo what you just did to the equilibrium mixture. Here's a good question, a little bit tricky. How will the equilibrium constant Kp, how will that be changed when the temperature is increased? And you know what? This is an important point. One of the very few things that can affect an equilibrium constant is indeed temperature. Warming it, cooling it, affects the rate constants forwards and backwards, and thus the equilibrium constant, K, EQ, Kc, Kp, they're all affected. So if I increase temperature, I increase this. And if I increase this, in a sense, I take some of this and I move forward to make more of this and more of this. So if I made more of this and more of this in the numerator of my equilibrium constant expression, then that would make this number go up larger as well. So the answer is it'll go up as well. Of course, everything's reversed. If you cooled it, the constant would be smaller, or if I switch this number over to the other side and imagine this reaction to be exothermic, then if I warm that up, then she would shift back away from that to create a smaller equilibrium constant. Oh my goodness. This takes some practice, some thought, some imagination. How will the equilibrium shift if a sizable quantity of helium is injected into the mixture? By sizable, I mean 2 moles, 1 mole. And the answer is helium is unreactive. Of course, I'm assuming that none of these are helium in a chemical reaction because helium doesn't react. So if I inject an inert gas or a gas that has nothing to do with equilibrium and does not interact chemically, then the answer is no effect. The balance will not be shifted. True, the total pressure increases, but not the partial pressure of each gas or the molarity of each gas, moles per liter, because I'm not shifting any amounts, and this ratio, this constant, is still in effect. So that's a trick question. Inert gases like helium, for example, or a gas that has nothing to do with the reactants and does not interact with the products or reactants, no effect. How will the equilibrium shift if a suitable catalyst is added to the mixture? Well, catalysts make things go faster, right? So the answer is, trick question, no effect. Catalysts might indeed help attain an equilibrium faster, but they have no effect on this constant, and they have no effect on the equilibrium amounts of products or reactants. So keep that in mind. Trick question. Catalysts don't affect the constant. They affect the rates, but they shouldn't affect the overall K. How will the equilibrium constant shift if the volume is compressed to half the original equilibrium's volume. Well, let's see. This is a tricky one as well. Decreasing the volume, I'm compressing the volume, so I'm building up the pressure, and nature doesn't like that. She was content with the 2 moles of gas here, 1 mole of gas here, 1 mole of gas here in an equilibrium to give Kp 0.11. Let's see. Yes, so decreasing the volume increases the pressure and the partial pressures in a sense because we're in a smaller space. So what nature will do is she'll try to go away from that. She'll try to shift away, do whatever she can to lessen that increased pressure that you're imposing upon her. True, I personify this Mother Nature stuff too much, and the only thing she can do to do that is to reduce the number of moles of gas. This side has 1 mole of gas. This side of the equilibrium has 3 moles of gas. So what she'll do is she'll take 3 moles of gas and shift them this way to create only 1 mole of gas. Or she can't go the whole way. This constant still likes to be in effect, but decreasing the pressure, decreasing the volume, increasing the pressure, indeed tries to minimize the number of moles of gas. So if one side of the vessel has, one side of the equilibrium has fewer moles of gas, it'll shift that way. And think about the opposite as well. If I increase the volume, I decrease the overall pressure, allowing more moles of gas to be formed, and so nature will try to attain that old pressure that she used to have. Instead of the low pressure, she'll want to go back to the high pressure, and again she'll shift this way, which is the opposite of what we just decided up here. Alright, what happens to the equilibrium constant as the volume is compressed? Trick question. Doesn't change anything. The constant stays the same. The volume is compressed, the pressures build, but the amounts shift in order to keep that Kp the same number. Oh, cool. Ta-da, done. Thanks guys for watching. See you in class. Good luck on the homework and such.